Okay, so the last video we just talked about, this table and sort of the tree sets are just vastly better at these sort of tasks, the set and dictionary tasks than lists. But, and big O's are sometimes hiding some details, and there might be a lot of work in there, and in practicality it might be different than the sort of made up numbers I gave here, but it's still a win. And so what's the catch? Well, the catch is that balancing that I talked about earlier. So this is what happens when a binary search tree is unbalanced, right? Search tree, the order still holds, but the balance is gone. And so this is totally unbalanced, right? To the right of B are 1, 2, 3, 4, 5, 6 things. To the left of B is one thing, right? 1 versus 6. That's very heavy, right? Its right hand is much heavier than its left hand. And so this is what happens when you pick a bad root, and also you don't bother to pick good roots in the subtrees as you go down. Since B does not divide the data evenly, we're kind of sort of messed up right from the get-go. We could do better than this with B as the root, but it's still pretty bad. And in the worst case scenario, right, a tree is just a linked list. Imagine root is A, and B is to the right of that, and C is to the right of that, and D is to the right of that, and E is to the right of that, and so forth, right? It's just a linked list. And then finding things, inserting things, becomes ON, because we have to find where it belongs either way. The other direction is always null, right? We can also imagine the backwards version of that, where H is the root, and then we go left 8 times until we get to A when we're looking for it. And so balancing is really, really critical. And so the trees that I've been drawing for you are balanced, right? And the way that we sort of look at this is we sort of look at how many nodes are to the left and to the right. And so D to the left has 1, 2, 3 nodes. D to the right has 1, 2, 3, 4 nodes, right? And we can sort of write these numbers on the rest of it. B to the left has 1 node. B to the right has 1 node. B is sort of more perfectly balanced even. A has 0 on each side. All the leaves have 0 on each side, right? We don't really have to do much work to count that. And so the node A is perfectly balanced, so is the node H in a way. G has 1 to the right and 0 to the left. F has 1 to the left and 2 to the right. And so you might say, hey, D, F, G are not super balanced, certainly in comparison to H, C, B, but being sort of like +1, as AVL would describe D and F and G, are not bad, right? Just because the last layer is not full, you're going to have some +1s, some -1s around, but that's not really a problem. A -2, where like on one side is 3 and the other side is 5, something like that is more unbalanced, right? So you just want to be as even as possible. And so we talked about how the complexity in this balancing are O log n, right? And we'll see some code for that in a bit. And there are a number of algorithms for self-balancing, be that the AVL tree algorithm, the red-black tree algorithm that Java uses, or the TREEP algorithm. And we will discuss these in a later lecture. Self-balancing algorithms are really algorithms topic and not a data structures topic. So we'll get the gist of them, but we're not actually going to code them up in this class. But you do have to know that balancing is very important because it's what gives us that log n behavior, right? It's what makes the depth, big O of depth, is basically the complexity of all operations in a tree that we care about.